Hello everybody. In the last few sessions we have been discussing about modeling electric circuits and also something about their analysis in MATLAB and also on paper. In modeling the electric circuits, we went through the process of obtaining the state equation, and then we use the state equation model to input to MATLAB and then see the results, the outputs in three domains, which is the time domain, the frequency domain and the pole zero domain. In this session, let us have a closer look at the pole zero domain. And a method of modeling called the transfer function modeling. It is again a special case of the state equation. As I told you earlier, the state equation will give you the overall total dynamic behavior of the system. It contains in it the information about the steady state model and also the transfer function model. We saw in the last session how we go about modeling for sinusoidal steady state conditions by replacing d by dt with j omega. In this session, we shall look at what is called as the transfer function modeling. I will explain what transfer function is later on as the class progresses. But we will see that it has a lot of useful features in studying the system in the pole zero domain and also to some extent in the frequency domain. So, today's session of course is going to be focusing on transfer functions. What are transfer functions, how they are obtained, this will be the focus of discussion in this session. If we look at the state equation of any general circuit or system, it is of the form dx by dt equals ax plus bu, and the output equation y is equal to cx plus du. This is the standard form of the state equation. This is the state equation. What is going to differ from system to system, circuit to circuit is the A matrix, which is the parameter matrix for the system, which defines the characteristics of the particular circuit, the B matrix or the input matrix, input scaling matrix, the C matrix, which is the output scaling matrix, and the D matrix or the feed forward matrix. This is the output equation, and the first one is the dynamic equation. If there are more than one states, x itself will be a state vector, x and if there are more than one input, u will be a state input vector, A will be a matrix, B will be a matrix, so also C and D. Now, this is the state equation that we know how to obtain for any given circuit. Now, if we look at the block schematic of this one, the state equation is basically composed of many first order linear differential equations. Now, if you look at the block diagram of this particular system, let us consider this here, the dynamic equation. So, you have the input, it is scaled by a B matrix or a B variable. So, it is given to a summer where one adds Ax. So, let us say that we have the parameter matrix of the system A here, and we are obtaining x from somewhere. So, you have here Bu and you have here Ax, and therefore, on summing it up you have dx by dt. This on integrating will give you x, and that x is fed back to obtain dx by dt. And if this x is fed through a scaling matrix C, one obtains Cx, and then if we have a summer here plus and a plus, and from this input u, let us pass it through a D matrix, one obtains y. So, starting from u here, the input variable, we get the output variable y, and intermediate, this is all what happens. This is a common block diagram for any system, because we are working with the general state equation. Now, what is important here to be noticed is that there is one integration and two summing blocks. The integration is fundamental to any physical system. Any physical system, as they can be represented as state equation, and the state equation has one integrator per energy storing element. So, the integrator can be used to model any physical system and also for simulating any physical system and thereby for analyzing. So, integrator becomes a very useful component in the physical system and physical block system or block diagram, where you can analyze and simulate the system. How do we how to represent an integrator? Where? In pole 0 domain, in the pole 0 domain. So, let us look at this first. This will give us an idea for using it for the other components. In fact, integrator being the basic fundamental building block, we will use this to model the other components like L and C's, and then thereby getting the model for the other complex circuits. In the pole 0 domain, we had two orthogonal axes like that. You have the sigma axis, which is the real axis, and we have the omega axis or the imaginary axis. And this complex plane is called the S plane. This is called the S plane. Note this variable S. This variable S is the same as the Laplace variable. The Laplace variable. The Laplace variable in Laplace transforms. So, this is also called the S plane, where the S variable S is equal to sigma plus j omega. Okay. This is how the pole 0 domain is represented. We saw that earlier. Now, we will see how to get the poles and the zeros from the electric circuits. Now, consider that we have an integrator, a block. I am just representing it a block, and it performs the integral action. There is an input and there is an output, and let us call the input as u and the output as y. Now, to represent this system in the pole 0 domain, we have to convert it into variables which are functions of S rather than functions of time. So, this whole domain, this is in time domain, we have to obtain a system in the pole 0 domain which are functions of the S variable or the Laplace variable, because the pole 0 domain is in terms of the S variable. So, how do we go about getting this? How do we go about mapping this? So, which means we have to transit from a system u which is equal to which is the input in the time domain, y which is the output in the time domain, and there is an integrated represented in the time domain, and this should be representable or represented as an integrator in the S domain with the input. So, u should be now a function of S, y, the output y should become a function of S, and this also should become a function of S. Then we say that this is in the S domain or the Laplace domain or the pole 0 domain, S domain or the pole 0 domain. Like that. Notice that I have replaced the lowercase u's by uppercase u, lowercase y by uppercase y. It is just a convention. All the variables in the S domain or the Laplace domain or the pole 0 domain, we represent it with uppercase. So, now we now would like to see what is y s by u s equal to. This will give the input output relationship in the S domain. The integrator by nature, if you look at the nature of the integrator, if you give a disturbance, it will accumulate. Basically, it will accumulate. Let us say I have here a waveform, wave shape like that as a function of time. When this is passed through the integrator, the output of the integrator is going to be this area. Okay. So, the output of the integrator will be like that. It starts accumulating the area, then the area is calculated, and then it keeps constant. The output never decays. Once the output has some value, there is no possibility for it to decay nor grow. So, which means whenever the input is 0, the output will just stay at its previous value. So, one of the main characteristic feature of the integrator is neither there is growth nor there is decay of the output. This is the special characteristic feature of the integrator. So, if we go back to the S plane, let us say I will write the S plane and you have the sigma and the omega, and this is the S plane. Okay. And let us say I have a pole there exactly at S equal 0 plus j 0. So, which means at this point, if I look at the time evolution, which we say is the exponential of e to the power of minus 0 plus j 0 into t, which is equal to 1. So, it is just a constant 1, no growth, no. If there had been a pole at this point minus a, then here it would have been e to the power of minus a t, a being some number other than 0, and therefore, here you will see that there is a exponential decay starting from 1. This will decay at a rate as defined by a, or if there is a value here b. Now, this is e to the power of b t, because b is positive, which will lead to exponential growth, and it will start growing as time progresses. So, a pole on the right of the S plane is going to lead you to exponential growth, which is unstable system. A pole on the left of the S plane is going to lead to exponential decay, it is a stable system. A pole which is on the j omega axis will neither cause decay nor growth, and a pole exactly at 0 is an integrator. In fact, if you take a variable which is a time function, let us say integral of x t, this, when I take the Laplace transform of this variable, will result in x s by s, or it is nothing but 1 by s x s, that is 1 by s and the Laplace transform of that variable. So, this represents an integrator, and this is at s equal to 0, which is what we have put the pole here. The denominator, the roots of the denominator are poles, roots of the numerator of any function which is function of s is the 0. Of course, here the numerator is just only 1, the denominator has a s value there, and therefore, it can be 0, that is this function has a root at the denominator equal to s is equal to 0, and that is a pole. So, at the pole value, when s is equal to 0, when you substitute s as 0, the gain is infinite. The gain of the function here becomes infinite between the input and the output. We will discuss the concept of the pole and 0, physical concept of the pole and 0 just a bit later, but now we have come to one important conclusion, that an integrator can be represented as 1 by s in the s plane or the pole 0 plane. So, this is time domain and this is the pole 0 domain or the s plane. So, now the integrator as such with the input u and output y can be represented in the pole 0 domain as now the input is a function of s u s, output is a function of s y s, and the integrator can be represented as 1 by s or y by s, the output by the input is 1 by s. In fact, this we call it as the transfer function of the integrator. Transfer function is defined as the Laplace transform of the output variable by the Laplace transform of the input variable under 0 initial conditions. Under 0 initial conditions. This is how a transfer function is defined, and what we got as the transfer function of the integrator, which is y s by u s, is 1 by s under the conditions that the integrator initial condition is 0. Now, we should be able to obtain the transfer function of any circuit, and the transfer function of the any circuit will be of this general form: y s output variable Laplace transformed, input variable Laplace transformed equals, it will have a numerator which is a function of s, a numerator polynomial, a denominator which is a function of s, a denominator polynomial. Now, the roots of denominator are pole locations in S plane. The roots of the numerator are 0 locations. They are the 0 locations in the S plane. So, that is basically the important concept in the case of the transfer function. It basically takes the time domain variables into the pole 0 domain variable or the Laplace domain variable, which is a function of S, and that results in a numerator polynomial and the denominator polynomial, the roots of which form the zeros and the poles. The roots of the numerator polynomial is the 0 locations in the S plane or the pole 0 plane, and the roots of the denominator polynomial form the positions or the locations of the poles of the circuit. Now, consider a capacitance. How do we represent the capacitance in the pole 0 domain or in the Laplace domain? We have a capacitance, we have a capacitance current which is flowing, and there is a voltage across the capacitance which is the state variable, which is V c. The dynamic equation is d V c by dt is equal to I c, or rewriting it, you have V c equals 1 by c integral of I c dt, that is now converted into integral. Now, if we have to represent it in the Laplace domain, how do we go about doing that one? Now, if we look at this, this is the dependent variable and this is the independent variable. So, we have a system here wherein you have I c which gets multiplied by 1 by c, passes through, because c is a constant, that passes through an integrator, and what you obtain is V c. Now, to convert it into the Laplace domain, what do? We change the case of the variables to uppercase. Now, instead of being function of t, it should become function of S. A constant still remains a constant even in the Laplace domain, and this is followed by an integrator in the Laplace domain becomes 1 by S, and this gives you an output which is uppercase V c as a function of S. So, this would be the mapping of the time domain block or the time domain equation into the Laplace domain equation or the Laplace domain block. Now, let us see that from this we have I c function of S 1 by c into 1 by S equals V c, which is a function of S, or V c by I c S function of S is given by 1 by S c. Compare this, with V c by I c functions of time which were equal to 1 by j omega c. This is for the sinusoidal steady state condition. This we had obtained for the sinusoidal steady state. And this is Laplace domain or the pole 0 domain. Now, notice the equivalence Notice the equivalence here. So, for the capacitive reactance, the j omega of the sinusoidal steady state is replaced with S to obtain the capacitive reactance in the Laplace domain. Likewise, for the inductor also, we have the inductor L, there is a state variable which is the current which is flowing through L, and there is the voltage across L, VL. Now, the dynamic equation for this is L DIL by dt is equal to the voltage across L, which is VL. Now, here the independent variable is the voltage across L and the dependent variable is IL, and IL which is equal to 1 by L integral of VL dt. So, we can rewrite this above equation, this differential equation in this form, so that we bring in the integral part there. And this can be written as, you have a VL input or the independent variable which is scaled by L, a constant, and this is passed through an integrator which is going to give you IL. So, this time domain process has to be reflected as a Laplace domain process by the following mapping. So, we call it as VL as a function of S, the constant parameters remain the same in all the domains. This is followed by an integrator in the Laplace domain represented by 1 by S, and this results in a current in the Laplace domain denoted by IL, a function of S. Let us just copy this portion. Copy, go to this page, paste. Now, here let us say IL, a function of S, by VL, which is also function of S, equals what? We want to obtain this. Okay. So, we know that VL function of S into 1 by L here into 1 by S is equal to ILS. So, this gives VL a function of S by IL a function of S, which is equal to SL. Or if we put it in this form here, IL S by VL S equals 1 by SL. Compare this with IL by VL, which is equal to 1 by j omega L, the reactance. Look at a very similar equivalence that arises. J omega, if it is replaced by S, j omega, which is in the sinusoidal steady state model, if it is replaced by S, then one obtains the Laplace model. Let us have a look at the simple circuit. So, if you have an RC circuit like this is an RC circuit with VI, R and C which has a VC here. Now, if we want to transform it to the Laplace domain or the S domain or the pole 0 domain, the circuit topology remains similar. We have the R, C, so we have V I which is now a function of S. Lowercase v has been converted to uppercase V, R remains as R, C will result in, here it was reactance which is 1 by j omega C, and here it will result in 1 by S C, and the voltage across C is now cap V C, a function of S. Now, this is the circuit which is now transformed into the Laplace domain, and if we perform the analysis on this, we will get the transfer function. For example, if we need to know, let us say V naught or V C, in this case V C S by V I S. This will give the relationship between the output V C and the input V I in the Laplace domain or the S domain. So, the analysis is performed in a manner similar to what is done with resistive network or in the case of sinusoidal steady state network. So, you have 1 by S C divided by R plus 1 by S C. So, the voltage across the capacitance is this impedance divided by the total series impedance in the Laplace domain. Or if we simplify this, you get 1 multiplying throughout by S C in the numerator and the denominator, you have S R C plus 1. Still further simplifying, we can write it as 1 by R C divided by S plus 1 by R C. So, this is the transfer function for this network, that is for this RC network. What does this mean or what does this imply? So, we have V C a function of S divided by V I a function of S, which is equal to 1 by R C divided by S plus 1 by R C. So, this is the transfer function between the input and the output, that is the transfer function of the output variable divided by the input variable is this. It has a numerator polynomial, there is no S term in the numerator polynomial, so there are no zeros. There is in the denominator polynomial an S term, that is there is S to the power of 1. This has a root. What is the root? At S equal to minus 1 by R C. At S equal to minus 1 by R C, if you substitute here, this will go to infinity. So, the gain goes to infinity, and that is a pole, because the roots of all the denominator terms will be poles, the roots of the numerator terms will be zeros. There is no s term in the numerator, so no zeros here for this circuit. You have the only one pole which is located at s is equal to minus 1 by R c, which means if I now draw the S plane. So, I have S plane, you have the sigma, you have the omega. So, this is the S plane. Now, S is equal to minus 1 by R c, therefore, this is 0. I take the negative real axis, somewhere here let us say we have minus 1 by R c. So, that is a pole location. So, this will be the pole 0 picture of the R c network. So, what does it mean? It means that when I have any disturbance or when I have any particular excitation and that excitation is removed, that excitation is going to decay at minus 1 by R c into t or e to the power of minus t by R c. So, it is going to decay with a time constant of R c. That is what it means when you talk of a pole. It means when I say I have a pole located at minus 1 by R c, it means that it is going to decay with the time constant of R c. If this pole starts coming closer to 0, then what is happening to R c? R c is becoming higher and higher till when it starts becoming close to infinity, this 1 by R c is at 0. So, which means that as it starts coming to 0, the pole, the decaying action becomes slower and slower, because R c time constant becomes larger and larger. Time becoming larger means it becomes slower and slower until at this point there is no decay, which is integral action. So, that is the integrator, and as this pole starts moving away from the omega axis, the R c becomes smaller and smaller, which means the time constant is fast, which means that any excitation, if after it is removed, will decay very quickly. So, that is basically the meaning of the pole location there. There is also another physical notion of the pole, which we will again discuss as we progress further in this modeling. Likewise, if we take the case of the inductor circuit, let us say we have a source, we have a resistance R and an inductance L. So, we have an inductance L, a resistance R, we have a VI, and then there is a state variable IL, which is here. Now, if this has to be shifted to the S domain or the Laplace domain, we will now have the circuit topologically very similar to what was there in the time domain. Only what is going to change is the way you represent the variables. So, it is VI, now it is S, R still remains as R. Now, the inductive reactance, what was given here is normally j omega L in the case of the sinusoidal steady state, the inductive reactance, and here it becomes S L. Now, if you want to find, let us say, the current through the circuit IL, and you would like to see what is IL by VIS. Now, that is nothing but voltage divided by whatever the impedance, which is R plus S L. So, the voltage divided by this is the system which gives you, if I rearrange the terms, 1 by L divided by S plus R by L. Here also notice that there is only a scaling factor in the numerator, there is no function of S in the numerator, and therefore, there are no zeros. In the denominator, there is a pole because there is a first order S there coming into the picture, and the pole is at S equal minus R by L, minus R by L. So, what it basically means is that if I have the S plane, sigma axis, the omega axis, this is the 0, S is equal to minus R by L, again the minus part of the real axis. I have a pole at some point here which is minus R by L. This again means that any excitation after it is removed will decay at minus R by L t, or the time constant here, which is t by L by R. L by R is the time constant with which this is going to decay in the case of the RL circuit. And here again, as the pole starts moving closer to 0, it means that either R is becoming 0 or L is becoming large. In effect, L by R is becoming large, which means the time is expanding, becoming large, and takes a much longer time to decay till the point at this point 0, where either L is infinite or R is 0, this point where there is no decay. And as you start going away from omega L, the L by R time constant starts decreasing and it starts decaying faster and faster. So, that is basically the meaning of that. So, if you take any arbitrary circuit, and let us take the RLC circuit, you have an R, you have an L, followed by, let us say, a C, followed by a C. So, you have Vi, so R, there is an L and a C, and you have Vc. Now, this you have to transform to the S domain or the pole 0 domain, and to do that we write this circuit again in the same fashion. We have a C, and this is, so the input Vi becomes Vis, a function of S, the output is Vc, a function of S, this is the input. R remains as R, the inductive reactance in the Laplace domain is Sl, the capacitive reactance in the Laplace domain is Sc, and you have your circuit in the Laplace domain. So, to obtain, let us say, the input output relationship, that is the gain between the output and the input, which is Vc by Vis, okay, the Laplace transform of the output Vc by the Laplace transform of the input Vi, which is going to give you the transfer function, which is here 1 by Sc, that is Vi into 1 by Sc divided by all the elements in series 1 by Sc. This is like a normal analysis that you would do with resistive network or sinusoidal steady state quantity network, and this is going to result in, if I make a slight simplification, 1 divided by S square L C plus S R C plus 1. So, here you see again no zeros, but in the denominator the S is of order 2. So, this is a polynomial of order 2 in S. So, therefore, this will have 2 roots, you will have 2 roots, which means 2 poles. There are no zeros, but 2 poles. So, the order of S will indicate the number of roots and therefore, the number of poles in, for the system. And if you write the S plane omega. So, there can be 2 poles, but of course, the location of the poles can vary. It can be 2 poles on the real axis, or it could be 2 complex poles. But if there is a pole on the a complex pole which is not on the real axis, there should always be a mirror image of the pole there to indicate that there are L and C components which are 180 degrees out of phase. So, this will give you location of, let us say, a general location of the pole. Now, here this projection on the real axis will give you the decaying action, will give you an idea about the decaying action, provided there is some excitation and the excitation is removed, and this will give you a notion of the frequency at which it will oscillate. So, let us say there is a excitation, a disturbance which is given and taken out, this will start oscillating, but the oscillations will decay. So, this decay of these oscillations is governed by this projection value here, and these oscillation frequencies are governed by this projection on the vertical axis of the S plane. So, this is a typical waveform nature of the RLC circuit, and this is called an underdamped circuit. Depending upon the positions of the poles there, one can get fully damped, that is no oscillations, to very large underdamped oscillations based on the locations of the poles here, which of course we will see a bit later. Now, what is important to note at this point here is that state equation is a complete description of the system along with the dynamic behavior, and out of which, under some constraints, we have shown that when d by dt is replaced by j omega, if the inputs are sinusoidal, then we can get the sinusoidal steady state equation from the state equation. Likewise, for the transfer function, because transfer function is under the constraint that there are no initial conditions, because state space has no such restriction. So, a transfer function should also be obtainable from the basic state equation. So, the state equation in the general form, we see that it is dx by dt plus equals ax plus bu. This is the dynamic equation, and the output equation is given by cx plus du. So, if there are more than one states, x is a vector, A is a matrix, y can also be a vector, and u can also be a vector for multiple inputs. So, this is valid for multiple inputs, multiple outputs. and for any number of states of the system, and for the case of the transfer function it is valid only for single input, single output. Now, how do we obtain the state equation for the case of for the case of any circuit where you have the equations given like this. So, the transfer function is obtained in the following manner. Taking this dynamic equation, we have S x s, because when we say integral is replaceable by 1 by s, d by dt is replaceable by s when the initial conditions are 0. So, you can say s x s is equal to a x s plus b u s, or s I minus a if it is matrix form x s is equal to b u s, or x s will be s I minus a inverse b u s. Now, if you consider the output equation y s equals c, for x s we will substitute this, that is s I minus a inverse b u s plus d u s, and we want to find the transfer function of the output by the input, the output Laplace transform of the output by the Laplace transform of the input, which is c s I minus a inverse b plus d. So, this is the transfer function obtainable from a state equation which has matrix A, B, C, D. So, given A, B, C, D matrices, you can obtain the transfer function also from the state equation. And once the transfer function is known, the roots of the denominator polynomial are the pole locations in the S plane, the roots of the numerator polynomial are the 0 locations in the S plane, and they give an idea about the damping properties, the decay properties of the system for any excitations and disturbances. We will of course be using the transfer function and the state equations both together interchangeably at various points of time in the discussion of the analysis of the circuits in future also. So, there will be a lot of usage of these transfer functions in the future discussions.